as the limits as theta goes to 0, and it's going to be of cosine theta minus 1 over e to the theta minus 1. So if we use direct substitution right away, what kind of indeterminate form would this be? Yeah, it'd be 0 over 0, because we plug in 0, we get 1 minus 1 over 1 minus 0 minus 1 is equal to 0 over 0. So we know we're going to have to use L'Hopital's rule, meaning we have to take the derivative of the top and the derivative of the bottom. So we have ddx of this cosine theta, sorry, not ddx, it'd be dd theta of cosine theta minus 1 divided by dd theta e to the theta minus 1. Derivative of cosine is going to be negative sine. Derivative of negative 1 is 0. So we're just going to have a regular negative sine theta on top. Derivative of e to the theta is just e to the theta. Derivative of negative theta is negative 1. Derivative of negative 1 is 0. So we're left with negative sine theta divided by e to the theta minus 1. Right, now that we have this new limit, we're going to use direct substitution and see if we get anywhere. We're going to end up with 0 over 1 minus 1, which is 0 over 0, so another indeterminate form. And we're going to have to use L'Hopital's at least one more time. Using L'Hopital's rule, we have the limits as theta goes to 0, and then we're going to have ddx of negative sine. Was it negative sine? Yeah, negative sine theta. Sorry, not ddx, dd theta of negative sine theta. And then we have dd theta of e to the theta minus 1. Derivative of negative sine is going to be negative cosine. And then the derivative of e to the theta is e to the theta, and derivative of negative 1 is 0. Okay, so now we're going to use direct substitution again. Plug in 0, we get cosine 0, negative cosine 0, divided by e to the 0, which is going to be negative 1 divided by 1, so it's going to equal negative 1. Meaning that our final limit as theta goes to 0 of cosine theta minus 1 divided by e to the theta minus 1 is going to be equal to negative 1. Yes, all of these example problems except for the one that's, we did one previously that's from 9.1, 9.2, 9.3. So except for that problem, all the problems come from the back of the textbook from 4.5. The other one I did get from the back of the textbook, but I changed it a little bit, so it's not going to be the same answer that's in the back of the book. The one we just worked out was number 43. We are going to move on to a little, I'm going to send the attendance links. I think a couple more people have joined. But we are going to move on to a little bit more of a difficult limit. Or at least I thought it was more difficult. Maybe you won't, but I thought it was a little more difficult. So this is number 61. And we're going to be using, or we're going to be finding the limits as x goes to infinity of x plus 2 divided by x minus 1 raised to the x power. Okay. So when we evaluate this, I'm not sure of this. Sorry, I'm trying to scroll back up to see where we wrote. I think we wrote our indeterminate form somewhere, but I think this would either be a 0 to the infinity. I think technically it's going to be a 0 to the infinity power, or I think that was one of them, but I think when I wrote it down, I wrote it as infinity divided by infinity to the infinity. I think that's technically not one of your indeterminate form, infinity to the infinity. I'm not sure how they treat that exactly. I think that'd be a great question for Dr. Noring. It does exist, but I'm not sure how they would treat it. I think it would probably just be infinity, but yeah. Like I think the answer to that would just be infinity if you end up with something like that. But anyways, even if the form you get isn't exactly like an indeterminate form that we have written, but we see that infinity divided by infinity raised to an infinity power, like we know it's indeterminate. And the reason why I said it could be 0 to the infinity is because of just the inside, but I'm not. It's a little. I'm not sure exactly how they determine the different forms, but that's personally what I would write for that one. I don't know if that's 100% correct, but the main goal for this is not which indeterminate form is this. Is can you see if it's an indeterminate form and then figure out how to manipulate it in order to use L'Hopital's. All right. So for this one, we are going to have to use our logarithms because we see we have this x in the exponent and then we have x's inside, right? That's kind of a key indicator that, okay, we're probably going to have to wrap everything in natural logs. So we're going to set our whole limit equal to a, x plus 2 divided by x minus 1 to the x, and then wrap both sides in natural logs. X plus 2 divided by x minus 1. Yeah, that's fine. All right, and then we can rearrange our limits, right, to get natural log of a is going to equal the limit as x goes to infinity of the natural log of x plus 2 divided by x minus 1 over x, or to the x power. And then we can use our logarithm properties in order to get, in order to bring that x out front. So we get the limits as x goes to infinity for the natural log, times x times the natural log of x plus 2 divided by x minus 1. Right? Does anyone remember what we would do from here in order to get this into a form that we could use L'Hopital's and evaluate? X on top. I think I understand what you're saying, but I mean, there's nothing more that we can do from x times the natural log unless we wanted to bring it back into this exponent area. But there's something algebraically that we can do in order to get this into like a full fraction. We could say that x is equal to 1 divided by 1 over x, right? Right. And that's something that you might have to use on the exam, right? Because if we use keep change flip, we have 1 times x over 1 is equal to x. So we can always convert that x into a 1 over x, or a dividing and then over 1 over x, which I don't like to do because, again, I hate ugly fractions, but it's kind of necessary for L'Hopital's in this scenario. Does that make sense why we're gonna use it as 1 over x? Yeah. Or convert it into that form? So if we have the natural log of a, we're still going to have this limit as x goes to infinity. And then we're still going to have this natural log. Yeah, kind of. So if you are multiplying something like if you end up with a limit that's like an x times something, whether it's like sine x or e to the x, it could be e to the x, or a natural log, a lot of times in order to get that into a form that we can evaluate with L'Hopital's rule, we have to convert that into something like, oh, this is sine x divided by 1 over x. Because then you see we can take the derivative of this top part and then the derivative of the bottom part. Yeah, no problem. I think it makes a little more sense when you visually see it, but that's just something that you need to keep in your brain. That's something that you're allowed to do whenever you're evaluating these limits. All right, so we're going to have the natural log of x plus 2 divided by x minus 1 over 1 over x, right? So now we're going to use direct substitution to evaluate this because this limit looks very different from our initial limit, and see what we get, right? Yeah, I think this form would technically be 0 to the infinity, I think. I'm not 100%. But when we use direct substitution, we'd end up with the form 0 over 0. And now we're allowed to use L'Hopital's rule for this one. But this is the part where I actually made a mistake when going through this. It'll be a lot better for us to use L'Hopital's rule if we simplify first. I guess we can apply L'Hopital's rule, right? So we still have this limit, x to the infinity, and then we have d dx, the natural log of x plus 2 divided by x minus 1, and then d dx of that 1 over x. So is there anything I can do to simplify that top part? Anything to do that might, where our derivative would look a little different than if we just took it as is? It'd make it a little bit easier on us as well. Remember our log property? Yeah, King, you're exactly right. Yeah, we would use that, our log property, ln of a minus ln of b. right, is equal to that ln of a over b. Sorry, that looks a little messy. But yeah, so you just undo that property, right? So we get the limits as x goes to infinity of d dx of this natural log of x plus 2 minus natural log of x minus 1. So it'll be a lot easier. We don't have to worry about our chain rule with this, really. Does that make sense? Because if we multiplied it, if we did it like that, we would have to then do the derivative of x plus 2 divided by x minus 1, which I think is a little bit much. All right, so now looking at these derivatives. Yes, yeah, this rule only applies to logarithms. The log rules are different from our other algebraic properties. They're kind of like this special thing. All right, so taking the derivative of that top part, we know the derivative of a logarithm is always going to be 1 over whatever is on the inside, right? So for our first one, we'd know we get 1 over x plus 2 minus 1 over x minus 1. And then we would multiply it by d dx of x plus 2, but we know that the derivative of x plus 2 is 1, the derivative of x minus 1 is 1. I don't think that we need to write that out. And then derivative of x, or 1 over x, so that's going to be the derivative of x to the negative 1, right? So just simplifying a little further, we'll bring down that negative 1, subtract 1, so we get negative 1 is x to the negative 2. Right, so we have 1 x plus 2 minus 1 over x minus 1 over negative 1 times x to the negative 2, right? So doing one last step of simplification, we are going to get 1 divided by x plus 2 minus 1 over x minus 1 over negative 1 over x squared. Whew. All right. So there's one more thing that I want to do before we apply L'Hopital's rule. And that is, I want to combine these two fractions. Right? I also, since we don't even know if we're going to need to use L'Hopital's rule again, we can bring that negative 1 over x squared to just be a negative x squared. Right? So we have the limits as x goes to infinity. So we have that negative x squared. And then we have our 1 x plus 2 minus 1 over x minus 1. Right, so how would we add these two fractions right here? I guess before I ask that, does how I got to this point make sense? I know we've been doing a lot of algebra for this problem, and it's a little tricky. All right. So we're going to add those two fractions together, and we're doing that by finding a common denominator. So we're just going to multiply both the 1 over x plus 2 by x plus 1 over x plus 1, and then we're going to multiply 1 over x plus 1 over x minus 1 by x plus 2 over x plus 2. So we're going to get that limit as x goes to infinity of negative x squared And then we're going to have x minus 1 over x plus 2 times x minus 1 minus x plus 2 over x minus 1 times x plus 2. And then we can combine those fractions since we found common denominator. And then we get this negative x squared times x minus 1 minus x minus 2 over x plus 2 times x minus 1. And then simplifying one more time, we get our limit as x goes to infinity of x, or negative x squared times negative 3 over x plus 2 times x minus 1. And then I'm going to go ahead and bring that. We see that those two negatives will cancel out. And then I'm going to bring that x squared up top. So we're going to get that limit as x goes to infinity of 3x squared over x plus 2 times x minus 1. Is there any questions on any of the algebra? Because I know we did a lot, and I know that's probably causing some people to leave, and I'm sorry about that. Or maybe it's just they don't have enough time. But I do want to make sure that you understand all the algebra that we just did. Yes, it's a lot, and I don't think you'll have one that's this complicated on the exam. But I do think that he might have one where you have to use that 1 over x property that I just did for the previous L'Hopital's, if that makes sense. And I mean, he might have one where you have to use that property. How would you rearrange it if it was subtraction without a log? So if it was just like x plus 2 minus x minus 1?
Oh, so hard.
So if it was x plus 2 minus x minus 1, we would just, and if we were trying to take the derivative of it, we would first just simplify it. So we would get x minus x plus 2 plus 1 equals 3. So we just simplify that top to equal 3. You would just do it like normal, simplify like normal. Well, I guess x minus sine x. You can't really simplify that further, so you would just take the derivative separately whenever you use L'Hopital's. So you would do the derivative of x and then the derivative of negative sine x. You can't really combine them. This kind of thing is really, I guess, I don't want to say only for this type of limit, but I don't know, I really did like this limit just because, yeah, I wouldn't put it in fraction form if it was just, that we only did that because of the logarithm, right? Well, initially we set our whole thing equal to natural log of a, and that's how we started with this fraction, and then we got it to two separate, right? So we started in this form, and then before we took the derivative for L'Hopital's rule, we got it into that form. I know we've spent a decent amount of time on this problem, so I kind of forgot what our initial one was too, but yeah. I can kind of talk through it after we're done to summarize. So when we're at this point, right, we say, okay, let's use direct substitution and see what we get. If we plug in infinity, we still see we're going to get infinity over infinity, meaning we still have to use L'Hopital's rule again. But this time we don't have to use that nasty 1 over x. We can just use regular derivatives. So we have to use the L'Hopital's rule. So we get the limit as x goes to infinity of d dx 3x squared divided by d dx of x plus 2 times x minus 1. For the top derivative, we're just going to use power rule, and for our bottom derivative, we are going to use product rule. Right? So for our top part, we get the limit as x goes to infinity of 6x. Now, bottom part, we still have to use product rule, so we have x plus 2 times d dx of x minus 1 plus x minus 1 times d dx of x plus 2. So simplifying, we get the limit as x goes to infinity, 6x, and then we end up with x plus 2 plus x minus 1. So simplifying, we get the limit as x goes to infinity of 6x divided by, so we have x plus x, that equals 2x. 2 plus negative 1 is going to be a positive 1. Right? So using direct, we get infinity over infinity still, so that means we still have to use L'Hopital's rule one more time. Okay, so we're going to get L'Hopital's rule, so we have the limit as x goes to infinity of d dx of 6x divided by d dx of 2x plus 1 is going to be equal to the limit as x goes to infinity of 6 divided by 2, which equals 3. That's not our final answer, but we did a lot to get there. I think we did 3 L'Hopital's rules and a ton of algebra. But you have to remember that whenever we did our limit, we said the natural log of a is going to be equal to this limit. So we know our natural log of a is equal to 3. So we know that a is going to be equal to e to the 3 power, meaning that this is actually the answer to our limit, right? So our final answer is this limit as x goes to infinity of x plus 2 divided by x minus 1 to the x is equal to e to the 3 power. No, you couldn't. You couldn't do that because you would get the wrong. I mean, it's possible that you'll get the right answer, but the way you evaluate it was still incorrect. Like, when you're using L'Hopital's rule, you have to have a top function and a bottom function. And I mean, if you were multiplying by 1 over x for this whole thing, I guess that would be fine, like if that was like the original problem. But since whenever we bring that x down, right, so we have that x right here, we bring it down right there. If we just said it was divided by x, that wouldn't be equal to what we have right here. Does that make sense? And that's why we have to divide it by 1 over x. It's just algebraic manipulation that we use so we were even able to use L'Hopital's rule. Yeah, if you can't write it in a way that makes it a fraction and the fraction equals 0 over 0 or infinity over infinity or something like that, then you're not allowed to use L'Hopital's rule. On this exam, obviously, you're going to have to use L'Hopital's rule on all the problems, but that won't be the case for all limits. It just kind of feels like that because all the limits we're doing are L'Hopital's limits, you know. But yeah, this one was a doozy. I hope you at least found it interesting, though, even if it's a little terrifying. So, I don't think you'll have that hard of a problem on the test. I don't think. I think that problem would take up too much time, honestly. Just for time wise, I don't think he would put that problem on the exam, but he might have something, where you have to use your log properties that we used in these problems, or like you have to use that 1 over x tool that I just talked about. Yeah, I did this problem just because I thought, like, if he does something that hard, hopefully it'll prepare you, and if not, it's good practice because you'll really understand limits if you can do that problem. Um, but we have time for maybe one or two more. None of them. What was 9.6 like? I have a couple more, but let me see what 9.6 was. 9.6. So 9.9, we did one like 9.9, sorry. 9.9. Let me look at the other ones I have left. I have one kind of similar to 9.9 that we can do. But yeah, after this I can talk through it. Let's not do 63, let's do 48. Alright, so this one's kind of similar to 9.9. I can talk you through 9.6 or 9.9 after. I don't have as long of a time to say, but I can quickly go through it. So for this limit, it's e to the x minus 1 squared over x sine x. And that's our limit, and it's as x goes to infinity. Or, no, as x goes to 0, sorry. My bad, as x goes to 0. So if we use direct substitution and evaluate it, we would get 1 minus 1 squared over 0 times 0, which would just be 0 over 0, which we know is indeterminate. So we're going to have to use we're going to have to use L'Hopital's rule. Not direct substitution, we're going to have to use L'Hopital's rule. Alright, so we're still having our limit, and then we're going to have d dx of e to the x minus 1 squared over d dx of x sine x. Right? So for our top one, we're going to have to use chain rule, and for our bottom one, we're going to have to use product rule. Okay? Always ask yourself before you take the derivative, is there some other rule that we have to use? And yes, Gabriel, you do need to write direct substitution. Or I don't know if he'll take off points or not, but I know that he wants you to write that whenever you're evaluating it. So I would write it. I didn't do that when I took Calc 1, but that's something that he wants, so I would just do it since he wants it. Yes, you have to. You absolutely have to write LHR, but yeah, I would write the DS whenever you actually input it, just to be safe. But yeah, I don't think it's that big of a deal, but I would do it because that's what Dr. Morin wants. So math teachers are always particular, like every single math teacher is, just in a different way. So for that top part, we're going to have to use L'Hopital's rule. Or not L'Hopital's rule, we're going to have to use chain rule. So we're going to bring down that 2. Then we're going to have that e to the x minus 1, and then multiply by the derivative of e to the x minus 1. I don't want to write that out, but the derivative of the inside portion would just be e to the x, right? Divided by, and then we have product rule, so we have x times the derivative of sine x, sine x plus sine x times d dx of x. Alright, so that would equal the limit as x goes to 0 of 2 e to the x times e to the x minus 1 over x. The derivative of sine x is cosine x. Derivative of x is 1, so x cosine x plus sine x. We have a new limit, meaning we're going to have to use direct substitution and evaluate. So we have 2 times 1 minus 1 over 0 times 1 plus 0. So that would equal 0 over 0, meaning we've got to use L'Hopital's rule again. So we have L'Hopital's rule, and so we're going to find the derivative of the top and the bottom. So our top part is going to be d dx of 2 e to the x times e to the x minus 1, meaning we're going to have to use product rule on that top part, and then dx of x cosine x plus d dx of sine x. Alright, so for product rule for that top part of the limit, we have 2 e to the x times the derivative of e to the x minus 1 plus e to the x minus 1 times d dx of 2 e to the x all over, and then we have another product rule, so x times d dx cosine x plus cosine x times d dx of x plus the derivative of sine x, which is going to be cosine x. All right, so simplifying that top part, we're going to have 2 e to the x times e to the x plus e to the x minus 1 times 2 e to the x over, over x. Derivative of cosine is negative sine, and then derivative of x is 1, so plus cosine x plus cosine x. All right, so we're still going to simplify. So multiplying those e to the x's together, we get 2e to the 2x plus, and then I'm going to distribute that 2e to the x to each of those terms to get still in the wrong pen color, to get 2e to the 2x minus 2e to the x over 2 cosine x minus x sine x. And then from here we can evaluate, or I guess we should simplify one more step to get that 4e to the 2x minus 2e to the x over 2 cosine x minus x sine x. But now we can evaluate using direct substitution. I mean, we could have before, I felt like it was best to simplify. So raising everything, or plugging in 0 for x, we get 4 times 1 minus 2 times 1 over 2 times 1 minus 0 times 0. So we're going to get 4 minus 2, which is 2, over 2 minus 0, which is 2, which equals 1. So we know our original limit, which was, as x goes to 0, of e to the x minus 1 squared over x sine x. It's going to be equal to positive 1. Any questions on this one? I know I went through it a little fast. I still hope that you got the gist of it. And is there any questions? I can talk through it if need be. But that is our last problem for today. So if you don't have any questions, feel free to leave. But yeah, thanks for coming, everyone. I do appreciate it. Feel free, or good luck on your test tomorrow. No problem. I hope this helped. Okay, yeah, that's okay, Stephanie. Come anytime during office hours. I'll be there. No problem, Gabriel. No problem, Carson.